Hello everyone, this is going to be my last video on this series. The task in this particular question is going to be one, frame assignment, frame assignment, all right? Then the age parameter table. Then we are going to find the Jacobian matrix, all right? And last, we will be analyzing the singularity points, all right? So 4 questions. Let's start with frame assignment. All right, we've got the base frame, right? Now, the origin of the next frame can be right here, right? Okay, the Z1 axis will be in the direction of translation that is generated by this joint, prismatic joint. And accordingly, the X1 axis will be such that, this is Z1, this is X1, such that, right, it intersects the Z0 axis, right, here, and it's perpendicular to both Z1 and Z0. Then, moving on to the next one. Usually, we all the time actually choose the origin of a frame in the joint, right? Okay, let's try to do it. Let's say this is Z2, okay? Now, the next step is to find the X2 axis, right? It can be either here, here, I don't know, upwards, downwards, and nothing else, right? But out of these 4, let's say, directions, we do not have any that intersects the previous z-axis, okay? So that's why I would rather transform the origin of this frame, right, somewhere here, okay? So Z2 will not be starting from this origin, but here. The origin of the frame will be somewhere here, okay? Because the X2 axis should intersect the Z1 axis. So this is Z2, and X2 can be, I guess, here, okay, perpendicular to X1. All right, I guess everything is fine. Now, for the last frame, we copied the previous Z axis, which is Z2, and it's directed in this direction, so Z3, and X3, as usual, should be perpendicular to both Z3 and Z2, and it should intersect the axis Z2. So obviously, this is going to be X3. So this is frame assignment. This is frame assignment, and we did it. Okay, so in the exam, you are supposed to draw this manipulator, right? Then you have to just assign all this frame. The 4 of these frames should be written on your drawing. Okay, let's now move to the th parameter table. All right, well, we have 3 joints, which means that the th parameter table will have 3 rows. Let's try to do it. Such a table. The first column basically represents the I, at the joint number, if you will. Then we have thetas, we have Ds, we have alphas and As. Okay. All right. Let's start off with a theta 1. The question for theta 1 is around Z0. How much I have to rotate the X0 axis so that it can align with X1 axis. So we have revolute joint. Automatically, we have to write down theta 1, the joint variable, theta 1. Okay? Then the next question, theta 2. Around Z1, how much I have to rotate X1 so that it can align with X2. Now, as you can see, they are already aligned. They are parallel. No matter what you do, just actuate this one, actuate this one, actuate this one. No matter what you do, they are always parallel to each other. Okay, that's why there is no need for any rotation around around Z1 axis. So we write 0 degrees for theta 2. Next one, theta 3. The question for theta 3 is around z2, right? How much I have to rotate x2 so that it can align with x3. Again, no matter what you do with these joints, they are always parallel to each other. That's why there is no need for any rotation around around z2 axis. Okay, let's move on to the next parameter, which is d. Now, d1, the question for d1, uh, along z0, like in this direction, along z0, how much I have to move or translate the origin of frame 0 so that it can align with the origin of frame 1. Okay, so we are asked to find this distance. Okay, previously it's here, now it's supposed to be here, so we have to move by this distance, d1. So let's write down d1 in this section of the table. Now, let's move on to the next D, which is D2. So the question for D2 is along Z1, along Z1 axis in this direction, how much I have to move or translate the origin of frame 1 so that it can align with the origin of frame 2? The answer is by this distance, D2. Let's write down D2. The next question for D2, D3, along Z2, how much I have to translate the origin of frame 2 so that it can align with the origin of frame 3? The answer is D3. Okay, sometimes some students get confused because of this particular length. Okay, but some literatures treat this let's say configuration differently. All right, let's assume this is given as A2. Some actual literatures treat it as D3 plus A2. But no, we don't do it here. We are actually over with we are done with only D3. We have to write D3 here because we assume that this A2 length is included inside D3. Okay, it's a joint variable. Now this is a joint variable. Joint variable, it kind of includes it. It contains this length inside, so we don't really care about that. Okay, but some literatures might treat this configuration differently. That's okay though. That's okay. Okay, let's move on to the next parameter, which is alpha 1. The question for alpha 1 is around this axis x1, how much I have to rotate z0 so that it can align with z1. As you can see, they are already aligned. They are parallel to each other no matter what you do. They will be parallel to each other all the time. So there is no need for any rotation. 0 degrees for alpha 1. Next one, here, alpha 2. The question for alpha 2 is around x2 axis, this axis, right? How much I have to rotate z1 so that it can align with axis z2. First things first, they are not aligned. So we have to have some rotation. But by what angle? Now, this is the question. And to answer this question, you have to first understand or find out, determine the direction of positive rotation. Okay? Now, this is x2, right? My right thumb will point this direction, x2, right? The curled four fingers shows the direction of positive rotation around the x2 axis, okay, which is this direction, okay, which is this direction around x2. Now, if z2 is rotated like that, for example, to this configuration, it was z0, now this is z1. If this is, and this is 90 degrees, right? If z0 is flipped to this, let's say, configuration, z1, right? Now it's going to be pi by 2. But unfortunately, I'm not rotating in this direction to make it align with z2. But you see that? I do not really rotate it here, but in the opposite direction, which is a negative rotation, right? So that it can align with z2. Okay, so that's why we have to write minus pi by 2 right here. Okay, let's move on to the next one, alpha 3. Alpha 3. The question for alpha 3 is around x3, around this axis, how much I have to rotate z2, z2, how much I have to rotate z2 to make it align with Z3? The answer is 0 because they are already aligned. No need for any rotation. Now, let's move on to the next parameter, which is A1. The question for A1 is along X1 in this direction, right? How much I have to uh, translate the origin of frame 0 so that it can align with the origin of frame 1. So I'm asked about this distance. This point, this particular origin, should be translated by this distance to make it here. Now the answer is A1. A1. Next one, A2. The question for A2, along X2 in this direction, right? How much I have to translate the origin of frame 1 so that it can be aligned with the origin of frame 2? The answer is 0 because they are already at the same point of X2 axis, right? So there is no need for any translation. 0 here. Next one, for A3, we ask ourselves this question. Oh my God, along X3, how much I have to translate the origin of frame 2, okay, so that it can be aligned with the origin of frame, what? Frame 3. Have a look at that. Both of these points are the 0th point of axis X3. So they're aligned all the time. So there is no need for any rotation. That's it. We have done the frame assignment. We have constructed the DH parameter table. Now, the next task is to find the Jacobian matrix for this 3 degree of freedom robotic manipulator. All right, let's try to do it real quick. Now, first things first, we have to determine the types of joints we have in the configuration. We have a revolute joint, we have a prismatic joint, we have revolute joint, prismatic joint, and prismatic joint. Okay. The Jacobian matrix is going to take the dimension of 6 by 3, 6 rows and 3 columns, and 1 column per each joint, right? So J of Q is supposed to consist of 2 parts: the linear velocity contributions and angular velocity contributions, right? Now, for the revolute joint, we write Z I minus 1 cross product P minus P I minus 1. So I is 1 in our case because this is the first joint. So Z0 cross product P minus P0, right? Now, for the angular velocity contribution, we have only Z I minus 1, which is Z0 in this case. Next column, we have prismatic joint. Now, the formula for prismatic joint becomes a bit different, which is Zi minus 1, where I is actually 2. So 2 minus 1 becomes 1, Z1, right? And it does not contribute anything to the angular velocity of the end effector. That's why we are supposed to write 0 right here. It's a vector 0, okay? Now, the next one, again, is a prismatic joint. So that's why we are going to have Z3 minus 1, because we have the formula was Z minus 1, right? And I in this case is the 3 because we are talking about the third joint, right? Now Z3 minus 1 becomes Z2, and here we have 0 because once again it does not produce any angular velocity at all, right? That's it. Now this is the general formula. Let's see what we have, what vectors we have in this particular formula. Let's see. Do we have Z0? Yes, definitely. Let's write it down. Z0 is always 0, 0, 1. Now, we know P0 always is 0, 0, 0, but we don't have anything else. We don't know anything about P. We don't know anything about Z1. We don't know anything about Z2. Let's find them out. Let's find them out. Now, to find it, to define or to determine the values of those vectors, we can use actually 2 methods. We can follow 2 steps. All right. One is geometric inspection. All right. If you do not feel yourself any more confident about geometric inspection, you can actually use the second method, which involves actual matrix computation. All right. One of these 2 methods, both are okay. It doesn't really matter which one you choose. Just try to be comfortable with the one you choose, okay? So it doesn't really matter which one you choose, okay? I'm gonna give you mark no matter what, okay? Let's move on and try to use the first method, which is geometric inspection. All right, but I'm gonna briefly talk about the matrix computation again, which has which has been um, which has been actually mentioned in my previous video on this channel as well. But still, I will touch this topic here too. All right. So um, first things first, I have to have a look at this picture from above. Right. This is my eye. This is my eye. And I'm looking at this picture from above. This is the angle of view. Right. So when I have a look at this picture, I see y0 and x0. I see the top of this revolute joint. I see this length, right? Top of this tiny prismatic joint. This small what length. Top of this prismatic joint and this length. All right, with the end effector. Now let's try to draw it. Let's try to draw. And you know what I'm doing here? I'm trying to find P using geometric inspection. Okay, let's try to do it. This is y0 and x0, y0, x0, all right? Oh, okay, so I have the revolute joint here. Now, the tricky part here is to define the angle theta 1, all right, properly and correctly. Now, to do it, you have to know the positive direction of rotation around z0 because theta 1 corresponds to this axis. Okay, theta 1 is the angle around z0, right? Okay, by which I have to rotate x0, okay, to make it align with the axis x1. All right, that's it. And what is the positive direction of theta 1? Theta 1, okay, my right thumb is directed towards, it's directed upwards, right? And the curled forefingers shows the positive direction, which is this one, okay, or this one, okay. Yes, okay. Now, this is x0, right? And I want to create such a triangle so that x1 can be here. Now, this is the link, this link, right? This link, and x1 is this. This is x1. And the angle between these two axes, x0 and x1, becomes theta 1. Now, this is how we define the angle in the geometric inspection method. Okay, so let's say this is x1, right? So automatically, it should be my A1 link, A1 link, this link. Okay, that's it, A1. What else? So this is positive theta 1. Then now, for now, I am ignoring this small thing because I told you in our methods we take this as a part of D3. Okay, so that's why I'm not going to draw it this way, like small indentation. Can I call it this way? No, small thing right here, and then the link itself, then the end effector. No, let's forget about this part. Okay, and I am drawing this from here up until here. Okay, what happens? That's it. Now this is point P. And what is this length? This length is D3. Okay, D3. That's it. Nothing else. Nothing else. Now, I guess everything is clear now. I am supposed to find Px. I'm supposed to find Py, okay, and Pz. Okay, we cannot see it. We cannot see Pz in this configuration. In this, let's say planar view, we'll have a look at this picture from a side. Okay, in this angle, and then it will turn out what PZ is. Now let's try to solve this problem. Now, what is PX? PX is this length of this particular side of this triangle minus this particular side of this triangle. Okay, so let's complete the picture. Okay, okay. Now this is theta 1 as well. This is theta 1. Okay, and that's why this becomes pi by 2 minus theta 1. Pi by 2 minus theta 1. Okay, now px becomes a1 times cosine of, sorry, did I write it right? Yeah, cosine of theta 1. Okay, now minus, I just found this one. This is a1 times cosine of theta 1 minus this length, which is d3 times cosine of pi by 2 minus theta 1. Now, overall, px becomes a1 cosine of theta 1 minus d3, right, sine of theta 1. That's it. That's it. This is px. Let's try to find the py component now. What is that? Py is this length plus this length, right? Am I recording? Yes, I'm recording. All right. Okay, and now this distance is, I'm talking about this one. This distance is a1 times sine of theta 1. Py becomes a1 times sine of theta 1 plus, from this triangle, this side, which is d3 times sine of pi by 2 minus theta 1, which in turn is cosine of theta 1, right? So that I can write it shortly, d3 times, well, cosine of theta 1. That's it. What about z1? What about pz? Sorry. pz, if we have a look at this picture from just the side, okay, in this angle, what do we see? Where is point P? Here, right? And this is the z0 axis, right? So I have to find the corresponding component of the point P on this axis here, right? And what is this length? d1, right? d1 up until here plus d2. Okay, because d2 has a contribution of point P along z0 axis. That's why pz becomes d1 plus d2. That's it. So I found this particular position vector. Okay, now p becomes a1 cosine theta 1 minus d3 sine of theta 1. Py is a1 sine of theta 1 plus d3 cosine of theta 1 and d1 plus d2. That's it. Now, again, we still are missing z1 and z2. And they can be found using geometric inspection too. All right. Now that's why I am drawing the same thing here. But obviously, okay, let's draw it. Let's draw it again using the same technique. Using the same thing. I'm repeating everything I did here. Okay. Now we have A1 here. Okay. Okay. Now we just stop here. Then we have this side, which is D3. Okay. Now, first things first. Z1 is this vector, right? The unit vector along this axis, Z1 axis, right? So no matter what you do, have a look at that. No matter what you do, like actuate this one. I mean, rotate it by whatever angle you want. Actuate disjoint by, I don't know, whatever D2 you want. Actuate disjoint whatever you by whatever displacement you want, D3, right? No matter what you do, the vector Z1, this vector, is always parallel to Z0, okay? It's always parallel to Z0. That's why Z1 vector, okay, will take the form 0, 0, 1. Because why? Since Z1 is parallel to Z0, they are going to be the same. 0, 0, 1. 0, 0, 1. That's it. Now, why did I tell you Z1 immediately? Because here I was supposed to draw X1, right? But I don't want to do it here. I don't want this picture to be more complicated than that. X1, the original is here. It's still here, but I don't want to draw it here. This is X1, right? But I don't want to draw it here because I want my picture to be more readable, All right. But what I'm looking is Z2, right? Z2. Where is Z2? Z2 is along what? Along this length, right? That's why Z2 can be drawn here as a vector, right? This is a vector Z2. This is a vector Z2. And what I'm looking for is its components along its projections, along X, along Y, and along Z. Okay, now let's try to do it. Now, it has two projections that can be drawn along Y0 and along X0, right? These two are its projections, okay? This is Z2 and its projection along Z0, and it is its projection along X0. Let me put it down. This is Z2 Y, and this is Z2X. Now, this part, this particular, let's say, vector, is going to be what? The unit length, which is 1, times, first of all, let me draw the angles too. This is theta 1, okay? This becomes theta 1 as well. This is pi by 2 minus theta 1. So if this is pi by 2 minus theta 1, it becomes theta 1. This angle is theta 1, right? So in this triangle, this side, this particular side is 1, which is the length of this side of the right triangle, 1 times what? Cosine of theta 1. And it's positive because the direction of this projection, okay, along which is projected, which is y0, right? Both of the axes have the same directions, upwards, all right? So that's why it's going to be positive cosine of theta 1. So cosine of theta 1. Good. Now, what about Z2x, the projection along x0? This one. Isn't it the same side of this triangle? This side of the same triangle? Yes. So it's going to be sine of theta 1, but with minus sign, because the direction of Z2x is the opposite to that of x0. That's why it's going to be minus theta 1, minus sine of theta 1, minus sine of theta 1 is my answer. What about what about its projection? Like, what about the projection of this axis, Z2, along the Z0 axis? Z0 is directed towards me, right? So of course, its projection is going to be 0. Okay? The projection of Z2 along Z0 axis is going to be 0. So finally, this was the last vector. It becomes cosine of theta 1 minus sine of theta 1 and 0. That's it. Nothing else. Nothing else. Okay? Now I have everything. I have all of these vectors here. I just found them. Then I can move on to the next one, to the next step, which is substitution of these vectors in this matrix formula. Now, let's put a pin here, okay? Because I would like to, I would like to remind you of how we can use the matrix computations to find the same, let's say, pieces of information. Okay, so if you don't know how a geometric inspection is done, if you don't know how this is done, you can use geometric inspection, which actually involves, where is my matrix? Where is my matrix? Oh my goodness. Okay, fine. Let me find it. Okay, I guess this is the one. Copy it. Okay. It requires this matrix. Okay. The second method, which is matrix computation, requires this matrix formula. Okay. Well, okay, you have Z0 already. You know, this is automatically, and immediately you have to write down this vector. Z0 is 0, 0, 1 all the time. P0 is 0, 0, 0 all the time. Now, what about P? How can you find P? We know that from direct kinematics. A 3 to 0 matrix, right, consists of 4 components. The 3 by 3 matrix are 3 to 0. The position vector 3 by 1, right, P, and 0, 0 here, and 1 here, okay? Now, this P is the same P, all right? What I want to tell you is, if you want to find P using computation of matrices, then you have to find this matrix, homogeneous transformation matrix, A 3 to 0. And how can you find it? By simply multiplying A 1 to 0 times A 2 to 1 times A 3 to 2. Okay, so what are these? This is basically 3 homogeneous transformation matrices, okay, that basically relates, let's say, 4 consecutive frames, okay? Well, this is the relationship between 0 and 1. This is the relationship between 1 and 2, frame 1 and frame 2. This is the relationship between, frame 2 and frame 3. Now, how can you find A1 to 0? Now, how can you find A1 to 0? Simply, you will use this one, this matrix, right? Have a look at that. Oops. You see A here, right? Sorry, you see A1 to 0 right here. So in this case, I is equal to 1. So in this formula, substitute everywhere 1 instead of I, okay? So it becomes A1 to 0 becomes cosine of theta 1, sine of theta 1, sine of theta 1, cosine of alpha 1, cosine of theta 1, cosine of alpha 1. Did you understand? So, but where can you find those theta 1 and alpha 1 and D1 and theta 1, A1 and stuff like that? How can you find it? From the DH parameter table. From DH parameter table. For example, the first row will be used to be substituted into this formula. Okay, that's it. Now, if you are supposed to find A2 to 1, right? I is equal to 2 now. Again, instead of i's, in this case, you have to write 2 everywhere, like 2, 2, 1 in this case. Now, what you have to do with the DH parameter table, you have to choose the second row. All right. Then, if you are supposed to find A3 to 0, 2, I is equal to 3 now, and instead of 2, you have to use 3, right? Instead of i's, you have to just replace 3 here, I is 3 now, A3 to 2 now, and you have to use the last row, the third row of the DH parameter table. Okay? Now, after you find all those matrices, you have to multiply them by each other, by one another. Okay? Then you are supposed to get A3 to 0, from which you can derive the vector P, which is used here. Okay? Now, okay, but we're not done yet, because how can you find Z1 though? Where is Z1? Here, right? Where is Z2? Where is Z2? Then, well, Z1 can be found from A1 to 0, okay? 1 to 0, okay? Okay, now this P1 to 0, let me put it this way, this P1, okay? You know what, sometimes you will have some problems where you are supposed to find, where you are supposed to determine P1 as well, okay? So this is exactly the same matrix that you have to have a look at to derive it, okay? P1, but where is Z1 though? Z1 is located inside this rotation matrix, okay? So what I'm about to tell you is the rotation matrix, this is the geometric matrix, right? For example, and P1 is something else. Let's say Px, P1x, P1y, and P1z, right? Now here we have some, whatever values. Let's say, what? Something, I don't know, A, B, C, then D, E, F. Then you will have 0, 0, 1. Okay, so when you find this matrix, using the first row of the DH parameter table and using the first row in this formula, okay, you get this one, right? You get something like that. And this column is Z1. Z1. I promise you this column will be the same as the geometric inspections Z1. Okay, they match. Okay, so if you have a question or a configuration of a manipulator, not like that, but something else, right? For example, if instead you have a revolute joint here, right? So the equation here in the second column will be Z1 cross product P minus P1, right? So where is P1? Now P1 can be found here. This is P1. Okay, that's it. That's what I wanted to tell you. Okay, what about Z2? This one is still missing. Now Z2 can be found from A2 to 0. Okay, which is multiplication of A1 to 0 times A2 to 1. Okay, so you know this one and you know this one because they are consecutive frame, let's say, transformation matrices. Multiply them, right, and you get A2 to 0. And you will definitely get the same thing, something like A, B, C, D, E, F, G, H, I, J, K, L, M, 0, 0 here, and cosine of theta 1 minus sine of theta 1, 0, and something here. Let's say P2x, P2y, P2, P2z, and 1 here. Okay? Again, I promise you, you are going to get the same result as the geometric inspection, as you did in the geometric inspection, okay, here as well. Okay, the results will be the same. That's it. So again, if you cannot follow these procedures that requires your geometrical skills, you can actually stick to matrix multiplication. And actually I gave an example to such a problem in my previous video too. So go back to it, all right? Try to understand, try to process the whole procedure and apply it here in this particular configuration of manipulator, okay? And see if you get the same result as the geometric inspection that I just did. Okay, now let's move on. The question was finding the Jacobian matrix, right? Now let's try to do it. So all we have to do is to substitute what? these values here. Okay, let's do it. So J is going to be equal to Z0, which is 0, 0, 1, cross product, P minus P0. Okay, P minus P0, P minus P0, P minus P0. Like element-wise, you have to subtract. Yeah, it becomes A1 cosine of theta 1 minus D3 sine of theta 1, A1 sine of theta 1 plus D3 cosine of theta 1, D1 plus D2. Then we have 0, 0, 1 here for Z0. I'm talking about that. Z1, what is Z1? This is Z1. What is Z2? This is Z2. And what is these zeros? 0, 0, 0, 0, 0, 0. Okay, let's write them down. 0, well, 0, 0, 1, 0, 0, 0. Again, cosine theta 1 minus theta 1, 0, 0, 0, 0. Now this is your Jacobian matrix. This is your Jacobian matrix, okay? All right. Now the next question is, oh, sorry. And of course you have to actually finalize the form because there's a cross product, right? So multiplication of these two elements minus these two elements becomes minus A1 sine of theta 1 minus D3 cosine of theta 1. Then A1 cosine of theta 1 minus D3 sine of theta 1. I multiplied these two elements and subtracted this one. And then A1 B2 minus A1, A2 B1. So it becomes 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, cosine of theta 1 minus sine of theta 1, 0, 0, 0, 0. That's it. That's it, y'all. And the next question is, find the singularity. Singularity. Now, what is singularity? Like singularity relating the linear velocities. Okay, linear, let's say, components and like contributions. Now, we have to choose. We have to choose the JP part, which is the linear contributions of the joint velocities to the velocities of the end effector. All right, so JP, and you have to find the you have to find the determinant of the JP part of the Jacobian matrix, and you have to equate it to, oh my goodness, equate it to 0. Okay, now determinant of this matrix is going to be, I'm going to take this one, so 1 times minus 1 over like third row, second column, 5 minus A1 S1 minus, okay, D3 cosine of theta 1, A1 cosine of theta 1, minus D3 sine of theta 1, and then we have cosine of theta 1 minus sine of theta 1, and it becomes minus what? Well, minus D3 cosine of 1 squared minus D3 sine of 1 squared. Now we have a trigonometric equality, and we have D3 being equal to 0. This is the singularity condition or point for the aforementioned robotic arm. Okay, now that's it for today. If you have any questions, comment down below or email me. It doesn't really matter. You can contact me on social media as well. And just note that this is the last equation in this series. Okay, sorry, this last problem in this series. I'm not going to upload any more videos. Okay, try to solve all of the problems that I have given you, all of the several problems, including the ones I have shown you in the series, right? And solve all the others whose solutions have not been revealed by me yet. Okay, I wish you good luck in your exam. Okay, I don't know. Have a good night. Have a good day. I don't know what time you are watching this video. I love you so much. Have a good day or night. Where is that? Okay. Ooh. Okay. Bye.